Alright, so welcome back to our class. So in this class, I'll be taking you guys momentum, which is a particular topic in phase 101. Okay, so these are the outlines. These are the outlines for today's class. Okay, so the very first part of this class, I'll be talking about momentum and impulse. All you need to know about momentum and impulse. Then after, we'll move to the conservation of momentums, where we talk about the applications. Okay, so talk about the applications, then move further to the coefficient of restitution before we do questions and answer. Okay, so now let's start with the class. Now, what is momentum and what do you understand by the word momentum? So the momentum of a body, the momentum of a body the moment of a body is the mass of that body times its velocity. Okay, let's say for example, now this is a body. Now for example, now this is the mass of this body, right? So the moment of a body is the mass of this body times the velocity of the body. Okay, so that is the meaning of momentum. The moment of a body is the product of the mass of that body. So the moment of a body is the product of the mass and what? The velocity of that body. Okay, so if the body does not have, when the velocity of a body is zero, therefore the moment of that body will be zero. When the mass of a body is zero, same also, the moment of that body will still be what? Will still be zero. Okay, so the moment of a body is the product of the mass. Let's say this is the body. The mass of this body times what? Times its velocity. Okay, so that is the meaning of momentum. Now let's continue. P, which is stand for what? P stand for momentum. Okay, so moment of a body is equal to the mass of that body times its velocity. Then don't forget that momentum is a vector quantity. Momentum is a vector quantity. There are also the SI unit. What is the SI unit of momentum? Now let's look for the SI unit. SI unit of momentum. What is the SI unit of mass? SI unit of mass is kg, right? Then what is the SI unit of velocity? Meter per seconds, right? So therefore, the SI unit for momentum is kg meter per seconds. Okay, so that is the SI unit for momentum. Okay, so let's continue. Now, according to Newton's second law of motion, we state that F is equals to m bracket to v minus u bracket close all over t. Now, if you cross multiply, you find out that first will be multiplying time, then we'll be left with m bracket to v minus u bracket close. So if you look at this part, you find out that ft is equals to what? Mass bracket open v minus u. So this quantity, this whole quantity here, everything here is known as change in momentum. Okay, everything known as what? Everything here is known as change in momentum. How is it change in momentum? Remember, if mass multiply v, we have what? Mv. If m multiply u, we have what? Minus mu. Remember, mass times velocity is what? Momentum. Mass times velocity is still momentum. So this is what? This is change in momentum. Now, what about this quantity here? Force multiplying time. Force multiplying time. This is known as impulse. Now, what is the impulse of a body? The impulse of a body is the time. Is the time it takes force to act. The time it takes force to act on a particular body. That is known as impulse. So impulse of a body is equals to what? Is equals to force times time. Okay, so the impulse of a body is the time rate it takes for a force to act on that body. When force is acting on a particular body, the time it takes that force to act, that's the time it takes the force to act on a body, that's known as what? That is known as moment, and that is known as impulse. So therefore, impulse is equals to force times time. Okay, so from Newton, we found out that from Newton's second law, okay, I can clean this part now. Now, you find out that from Newton's second law, which is law of momentum, Newton's second law is also known as law of momentum. Okay, so Newton's second law of motion is also known as law of momentum. Okay, so from Newton's second law, find out that F is equals to M bracket to move V minus U bracket close. Now if we cross multiply, find out that force multiplying time is equals to M bracket upon V minus U, right? Remember, I told you guys that everything here is known as what? Known as change in momentum, right? And this is known as change in momentum. While this part is known as what? Force times time is known as what? Impulse, right? So therefore, this part is known as what? This part is known as impulse. Impulse is equals to force times time. So that's to tell you that impulse equals change in momentum. Impulse equals what? Change in momentum. So impulse equals change in momentum. Now, where is the SI unit for impulse? Let's look at the SI unit. Now, where is the SI unit of force? SI unit of force is Newton, right? SI unit of time is what? Is seconds. So this is the SI, this is the unit for impulse, right? Remember, momentum, the SI unit for momentum is what? Kg meter per seconds, right? So that's to tell you that impulse equals change momentum, right? So that's to tell you that Newton seconds is the same, is equal kg meter per seconds. So therefore, if they may ask you what is the SI unit of momentum, you will say, we know that the SI unit of momentum is what? Kg meter per seconds, right? Yes. Also, the SI unit of momentum is still Newton seconds, because when Newton seconds equals kg meter per seconds and vice versa. So in summary to this first part is that momentum of a body is the product of the mass of that body and its velocity. Remember, momentum is a vector quantity. Then the SI unit of momentum is kg meter per seconds. Now I've also told you guys that it can also be Newton seconds, because where kg meter per seconds equals to what? Newton seconds. Then we also talked about impulse. And I told you guys that the impulse is the time it takes force to act on a body, right? And what is the SI unit of impulse? Newton seconds. And apart from that one, take note that impulse is also a vector quantity. Now let's move to this next part, which is laws of conservation of momentum. Now, law of conservation of momentum states that in an isolated system, change in momentum, change in momentum before collision, okay, in an isolated system, change in momentum before collision equals change in momentum afterwards, after collision. So this is this law of conservation of momentum, which said that in an isolated system, change in momentum before collision equals change in momentum after collision. Now these are the application of this law. Okay, these are the application of this law. One of the application is collision. The second application is recoil of a gun. The third application is rocket propulsion. Okay, so now let me first talk about rocket and recoil of a gun. Okay, because collision and rocket propulsion, we will talk about them soon. So let's talk about recoil of a gun. Remember, in conservation of momentum, state that the change momentum before collision equals change momentum what? After collision, right? Yes. Now, where is recoil of a gun? What is recoil of a gun? Now, for example, let's say if you fire a gun, for example. If you fire a gun, for example, you find out that the bullet usually moves to this direction, right? Yes. Now, if you fire a gun, the gun will usually move the relative velocity backward. I don't know if you understand. That movement backward is known as what? Is known as recoil of a gun. And this process is a conservation of momentum. Momentum is usually conserved in this process. Okay, so recoil of a gun. Whenever you fire a gun, you find out that the gun will move with a relative velocity backward. So that backward movement of the gun is known as recoil of a gun. Okay, now how does recoil of a gun applies to the laws of conservation of momentum? Now let's do it. Okay, now remember, conservation of momentum said that change in momentum. Change the momentum. Okay, since we are using recoil of a gun now, change the momentum before firing the gun will equals what? We equals change in momentum. Because we change momentum afterwards, after firing the gun, right? After firing the gun. Okay. Change the momentum before firing the gun. Before firing the gun. We equals what? Change the momentum after firing the gun. Okay. Now, since in this system we are dealing with two bodies, right? We are dealing with the gun as well as what? As with the gun and the bullet, right? With the gun and the bullet. Okay, let's say let's say let's take M1 as, okay, let's take mg as the mass of the gun, okay, as the mass of the gun. Then we'll take vg, okay, or let me just take m1 as the mass of the gun. Then we take u1 as the initial velocity, okay, as the initial velocity of the gun, right, of the gun. Then we take m2 as well, the mass of the bullet, okay. Then u2 as well, the initial velocity of the bullet, right, of the bullet, okay. Okay, so let's take M1 to be mass. Since we are dealing with two bodies, the gun and the bullet. So take M1 to be the mass of the gun, U1 to be the initial velocity of the gun, then M2 to be the mass of the bullet, then U2 to be the initial velocity of the bullet, right? Yes. Now change in momentum. Remember, conservation law of momentum say that in an isolated system, change in momentum before collision equals change in momentum after collision, right? Since we are dealing with the recoil of a gun, change in momentum before firing the gun equals what? Change in momentum after firing the gun, right? So what happens before we fire? Let me just come on here. Okay. So we'll come back to this place later. Now, change momentum before firing the gun. Now, before we fire the gun, this would be okay. Let's take this. This would be the mass of the gun. Then times it, the mass of times the velocity of the gun plus the mass of the bullet times its the initial velocity of the bullet. Then is equals to what? The mass of the gun as well, right? Then the final velocity of the gun. Then plus mass of the bullet times the final velocity of the bullet. Okay, so this part here is known as what? This part here is known as change momentum. It's known as change in momentum. Now change momentum before we fire the gun, right? Before firing the gun, right? Yes. Why this one known as what? Change in momentum afterward firing the gun, right? Yes. Now this, in fact, this applies to what? The laws of conservation of momentum. We state that change in momentum before collision equals change in momentum after collision. Since we are using the recoil of a gun to be what? Change in momentum before firing a gun, will cause to what? Change in momentum after firing the gun, right? Yes. Don't forget, this is the mass of the gun, initial velocity of the gun, mass of the bullet, initial velocity of the bullet. This V1 is what? We all know that this is the mass of the gun. This will be what? The final velocity of the gun, mass of the bullet, final velocity of the bullet, right? Yes. Now, initially, before we fire a gun, let's say for example, this is a gun now, for example. Now, initially, okay, the gun has mass, right? Yes. The bullet also has a mass. We all know that, yeah, bullet also has a mass initially, right? Now, what about their initial velocity? Initially, the gun is not moving, right? So before you shoot a gun, you hold the gun is not moving, right? So therefore, the initial velocity of the gun is 0, right? So it will be m1 times 0, right? Then plus, don't worry about the initial velocity of the bullet. Now, initially, before you fire a gun, the bullet is usually stationary as well, right? Therefore, here will still be what? 0, right? So 0 times m1 will give us 0. 0 times m2 give us 0, right? So therefore, we'll be left with what? M1 v1 plus m2 v2, right? Now that is initially before you fire the gun is usually stationary. The bullet is also stationary. Okay, but after you fire the gun usually move back with a particular velocity, which is known as recoil velocity. Then the bullet will still move, right? The bullet will move forward with a very high velocity, right? So therefore, initially the velocity of the gun and the velocity of the bullet is zero. Therefore, initially change momentum before we fires the gun is what? Is zero. Okay, so the change momentum before firing the gun is what? Usually zero, right? Yes. Okay, so after we fire the gun, the change momentum after we fire the gun is this, right? M1 V1 plus M2 V2. Okay. Now remember, this is the mass of the gun, this is the final velocity of the bullet. I mean the mass of the gun, final velocity of the gun, mass of the bullet, final velocity of what? Of the bullet, right? Yes. Now recoil of a gun, remember I told you guys that recoil of a gun is that backward speed or that backward velocity. Remember when you fire a gun, for example, there is this backward velocity with which the gun move backward. So that backward velocity is known as recoil, velocity. Okay, it is that final velocity of the gun with which the gun moves back when we fire the gun, right? Yes. Therefore, now in question we ask us to calculate for the recoil velocity of a gun. We have arrived something like this, that according to law of conservation of momentum, we said that change momentum before firing a gun equals to what? Change momentum after firing the gun, right? Before we fire the gun, change momentum is zero. After firing a gun, we find out that change momentum is equals to like this, right? Yes. Now this is the what? This is the recoil velocity. In question, they ask us to look at recoil velocity. Now we're going to look at recoil velocity is okay, look at recoil velocity is very easy, right? So we make V1 stand alone. So I'm going to make V1 stand alone. Okay, so we either take this, let's take this one to this side, but I take this one to this side or take this one to this side anyways. So if we take this part to this side, we arrive with something like this, minus M2. I'm coming. If we take it, cross it to this other side, we have this plus return to minus, right? So we have minus, I'm coming, we have something like this, minus M2 V2, right, equals to what? M1 V1, right? Yes. Since we're looking for V1, we have to start by what? M1, right? We have to start by M1. So if we cancel, we arrive with V1 is equals to 1 minus M2 V2 all over what? M1, right? Yes. So this is the formula to calculate for. So this is the formula to calculate for the recoil of a gun. Remember, this negative shows that the gun usually moves, backward towards the negative x axis, right? So this negative shows that the gun moves backward. So this is the formula to calculate for the recoil velocity of a gun. This M2 is the mass of the bullet, V2 is the velocity of the bullet, while M1 is the mass of the gun, while V1 is the velocity of the gun with which the gun moves backward, and this velocity is known as what? Recoil velocity. So that is all about recoil for a gun. Okay, now move to collision. Okay, move to the next application of conservation of momentum, which is collision. Okay, which is collision. Okay, take note of this formula. This is the formula for recoil of a gun. Okay, so collision is also an application of collision is also an application of conservation of moment, right? We talk about recoil of a gun. Now let's talk about collision before we talk about rocket propulsion. Now there are three types. You all know the meaning of collision. Collision means dashing, right? Yes, dashing. So now there are three types of collision. Okay, we have one, the elastic collision. We have two, inelastic collision. Then we have three, perfectly inelastic. Okay, so collision, there are three types. Okay, there are three types. We have one, elastic collision. We have two, inelastic. Then we have three, perfectly inelastic. Okay, so now what are the difference between elastic collision, inelastic collision, and perfectly inelastic collision? Okay, so now let's start with elastic. So take note that In an elastic, please take note, this is very important. In all types of collision, either elastic, inelastic, or perfectly inelastic, in all types of collision, momentum is always conserved. Okay, very important. In all type of collision, momentum is always conserved, right? Momentum is always conserved in all types of collision. Okay, in all types of collision, momentum is always conserved, but kinetic energy is not always. Okay, it's not always conserved. Okay, so in all type of collision, in either elastic or inelastic or perfectly inelastic, momentum is always conserved in either in any of them, but kinetic energy is not always conserved. Okay, so take note that now let's start with elastic. Okay, so elastic collision. Now what happens in elastic collision? In elastic collision, momentum is what? Momentum, this symbol for momentum. Momentum is what? Is conserved, right? Very important. Momentum is conserved. The kinetic energy is also conserved as well. Okay, so in elastic collision, momentum is conserved and kinetic energy is conserved. Now, this type of elastic collision, and now the reason why kinetic energy is usually conserved is because, let's say when the two body collide, there is no loss in total kinetic energy after the collision. Now before the now the kinetic energy, elastic collision, kinetic energy in elastic collision is always conserved because why? There is no loss of energy before and after these two bodies. Before they collide, the kinetic energy before they collide and after they collide, there is no loss in kinetic energy. Okay, so that is why kinetic energy is conserved. Remember, momentum is always conserved, right? Yes. Now this type of collision is usually found in gas molecule. Let's say in a cylinder, for example, in a cylinder containing gas molecule, all these gas molecules, they are constantly colliding with each other. So this type of collision of gas molecule is known as an elastic collision. Okay, so in elastic collision, the body's momentum is conserved, kinetic energy is conserved. Some collision is found in gas molecule. Okay, yes. Once this body collide, once they collide, they separate. Okay, yes. Then in inelastic collision, momentum is still conserved. Okay, now let's talk about inelastic now. In inelastic collision, momentum is conserved while kinetic energy is not conserved. Okay, yes. In momentum is conserved, kinetic energy is not conserved. This is because kinetic energy, because before this bodies, before they collide, the kinetic energy before they collide is different from kinetic energy after they collide. Okay, so there's usually loss of kinetic energy. The reason why kinetic energy is not conserved in inelastic collision is because of loss of energy in the form of heat, sound, deformation. Okay, now let's say, for example, let's say two cars collide together. Let's say two cars collide together. There will be a release of heat normally. Yes, sand energy will be lost in the form of heat, sand, as well as deformation. When they collide, the bodies are usually some part the body will usually deform. Yes, there will be a deformity in the bodies. Okay, so in inelastic collision, momentum is conserved, kinetic energy is not conserved. Then and the reason why kinetic energy is not conserved is because of loss of energy in the form of heat, sand, deformation. Okay, yes. Now, what is different between inelastic and perfectly inelastic? Now, both of them, momentum is conserved. Okay, in perfectly inelastic, momentum is conserved. Kinetic energy is not conserved as well. Now, the difference between inelastic and perfectly inelastic is that after collision, the two bodies stick together. Okay, so this is very important. Okay, in perfectly inelastic, after they collide, the bodies they will stick together and move with a common velocity. Okay, so that is the difference between perfectly inelastic from inelastic. Okay, yes. Now for elastic, when the bodies collide, they usually bounce off. right? Yes. Then in inelastic, the body, some of them they collide, then they might also bounce off. Okay, but there's only loss of energy in the form of heat, sound, and deformity. But in perfectly inelastic, once they collide, the two bodies they stick together and they move with a common velocity. Okay, so now let's what is the formula used to that can use to calculate for uh, under elastic collision, inelastic collision, as well as perfectly inelastic collision. Okay, now under elastic, okay, very important. Under elastic momentum, according to the laws of conservation of momentum before collision, change of momentum before collision is equals to what? Change of momentum afterwards, after collision, right? Yes. So before collision, under elastic collision, m1u1 plus m2u2 is equals to what? m1v1 plus m2v2. Okay. So this is the formula that we ask you to calculate. This is formula to solve elastic collision. Okay, this formula to solve for elastic collision. Then for the kinetic energy will be half m1 v square m1 u1 square plus half m2 u2 square, then is equals to half. And remember, kinetic energy, formula of kinetic energy is what? Half mv square, right? Yes. So initial of this one, we just need to add half, then square to the velocity. Okay, half m1 v1 square, right? Then plus half m2 v2 square. So this is for the kinetic energy. Okay, under elastic. Okay, yes. Then same also, okay, yes. Then same also for inelastic. Inelastic, based on the fact that momentum is always conserved in all type of collision. The momentum before collision will be m1 u1 plus m2 u2 equals to m1 v1 plus m2 v2. So momentum is always conserved. Okay, so this is for inelastic collision. Then what about for their kinetic energy? Okay, so we put what under inelastic now, half m1 u1 square plus half m2 u2 square is equals to half m1 v1 square plus half m2 v2 square, right? Remember, this v is their final velocity, u is their initial velocity. Now I'm not done yet. Okay, for the kinetic energy, based on the fact that in inelastic um in inelastic collision, energy is usually lost, right, in the form of heat. So plus q, okay, yes, half m1 v1 square plus half m2 v2 square, then plus q. This q is loss of energy in the form of heat. Okay, so this is the kinetic energy you calculate for inelastic collision, while this one is for elastic collision. Then what about perfectly inelastic? Okay, so for perfectly inelastic, momentum is also conserved. Okay, now remember, what did I tell you guys under perfectly inelastic? Under perfectly inelastic, the two bodies, they after collision they stick together and they move with a common velocity. Okay, so before collision, u1 m1 u1 plus m2 u2, right? Now after collision, the two bodies they do what? They usually stick together and they move with one velocity. Okay, that velocity known as common velocity. So therefore m1, it will now be what? m1 plus m2 bracket open bracket close times what? V. Okay, because they now move with the common velocity. Okay, so this is for what? This is for perfectly inelastic. This formula is this is for perfectly inelastic. Okay, yes. Now what about their kinetic energy? Okay, so kinetic energy now for their own kinetic energy before collision. Before collision will be what? Will be okay, kinetic energy before collision will be it will be m1, okay, it will be half m1 u1 square plus half m2 u2 square. That is before they collide. This part is after they collide, right? So this is the kinetic energy before they collide, right? Now what about after they collide? Okay, the kinetic energy, remember, they now move with a common velocity after they collide. So the kinetic energy after they collide, kinetic energy after after collision will be equals to will be half. Okay, since this body they now since after collision they collide together, right? So it will now be half bracket open m1 plus m2 bracket close v then square. Okay, so this is kinetic energy after collision, then this is kinetic energy before collision. So before we continue with this formula to see in the board, there's something I want to tell you guys. Remember, I told you guys that the moment of a body, P, this that is symbol for momentum, okay, is the mass of that body times its velocity. Okay. For example, now let's say this is the body now. The body is moving in this direction. Okay, the moment of the body will be what? Will be the mass of this body and what? And its velocity, right? Yes. Okay. Now, in this type of in this type of in this type of movement, the body is moving in where? In the positive S direction, right? The body is moving in the positive S direction. So that's to tell you that the momentum here is what? Usually positive. Okay. Yes. So this is positive momentum. Momentum is positive. Now, what if the body is moving in the negative S direction? Okay, the body moving in negative S direction. Therefore, the momentum will be what? The momentum will be what? Will be negative. Okay, because of what? Because of the velocity. Because moving in negative S direction, velocity will be negative. Therefore, the velocity will be negative. Therefore, the momentum will be what? Will be negative. Right? The momentum will be negative. So that is just it. Now, if the body is moving towards this direction, now this type of motion is in one dimension. Okay, this type of motion is one dimension. So if the body is moving in the positive S direction, the momentum, the velocity will be positive. Therefore, the momentum will be positive. Now, but if the body is moving in the negative S direction, the velocity will be negative. Therefore, the momentum of that body will be um negative. Okay, so please take note of these two. They are very important. For example, they say for example, they say two bodies are moving towards each other, one with a velocity of let's say 2 in the negative S direction, then the other one with a velocity of 4 in the positive S direction. So that's to tell you that the body moving towards this side has negative momentum, while the body moving towards this side has a positive momentum. So now let's continue with this equation you see on the board. Okay. So now these two equations, you can use this one is under elastic collision. Okay. So whenever they ask you, please just take note of the formula. Okay, v1, then v1 equals to bracket open m1 minus m2 bracket close divided by m1 plus m2 multiplied by u1, then plus 2m2 divided by m1 plus m2 bracket close multiplied by u2. So yes, these two they are different. Okay, so please take note of this formula. Okay, so this one is used to calculate for the final velocity of the first body, while this one is used to calculate for the final velocity of the second body. Okay, so these two formula is used under elastic collision when they say, for example, when they say two bodies they collide, then elastic they undergoes on elastic collision, calculate their final velocity. So this v1 used to calculate the final velocity of the first body, this v2 used to calculate for final velocity of the second body. So these are the two equations you need to use when they ask you to calculate for final velocity of the bodies. Okay, v1 v2. So that is just it. So please take note, we are going to use them to solve later. Okay, so please take note of this equation, it's very important. Now let's move to rocket propulsion, which is also another applications of conservation of momentum. Laws of conservation of momentum. Laws of conservation of momentum state that in an isolated system, change of momentum before collision equals change of momentum after collision, right? Yes. So now under rocket propulsion is also another application. Is also an applications of it's also an applications of conservation of momentum. Okay. Now these are also these also are the formulas we are going to use to solve for questions regarding rocket propulsion. Now let me explain everything so that you understand better. Okay, so let's explain everything now. Now let's say this is a rocket. Okay, let's say this is a rocket. Now let's say this is the part that contains the fuel, Remember, rocket don't require rockets usually use liquid fuel. Yes, that is in space, okay, because in space there is no air. So that is why they usually take liquid fuel with them. Okay, so now let's say this is a rocket. Now this is the part that contains the fuel. For example, this is part that contains the fuel. Now this is the now this rocket that has not been launched yet. Okay, now let's say this is the same rocket. I'm coming. And this is also the same rocket. Okay, all right. So now this rocket before it's launched, initially before it's launched from the ground. Okay, initially before this rocket is launched from the ground, please. Now initially when rocket is launched from the ground, let me explain everything. Let me explain how it is and all. Now the total mass of the rocket um is both is m, okay, capital letter m. So which is okay, if you look at this place here, m is different from the m, oh, please, is different from the m. So m, okay. Now this is the total mass of a rocket before it is launched. Now this total mass of the rocket involve is both what is both the mass of the rocket itself plus what the mass of the fuel. Okay, so this is the total mass. Total mass of rocket initially before the rocket is launched contains both the mass of the rocket itself plus the mass of what of the fuel, right? Of the fuel, right? Yes. So that is m. Okay. So that is before the rocket is launched. Okay, that is initially before the rocket is launched. So since the rocket is not launched yet, the velocity of the rocket will be what? Will be zero, right? The velocity of the rocket initially, right? Velocity of the rocket will be zero, right? Yes. So the velocity of rocket is different from the v. Okay, the minus v here. I will also explain that one for you guys. Okay, so now this is the now before the rocket is launched, that is initially before the rocket is launched from the ground, this is the mass, right, of the rocket. This mass is both the mass of the rocket itself and the mass of the fuel, right? While this one is the velocity of the rocket, right? Which is zero because the rocket is not being launched yet. Okay, let's continue. Now once the when we once we launch the rocket starts moving. There will be this fuel. Let's say this fuel will start burning little by little, right? As the rockets ascend upward, as we launch the rocket, the fuel will start burning, right? This is very important, okay? Before we start burning little by little, right? So now this is the exhaust, right? So the fuel will be burning with a velocity known as with respect to the rocket. This velocity is known as um this velocity is known as exhaust velocity, which is VE. Okay, this V subscript E. I'm coming. V subscript E is known as the exhaust velocity. Okay, exhaust velocity, the velocity with which the velocity with which the fuel is burnt, be burnt. Okay, yeah. So this V is what is the exhaust velocity, right? Yes, in this direction, right? Yes, with respect or relative to the rocket. Now, remember, before the rocket was launched, the fuel is not reducing. Before we launch the rocket, the fuel is not reducing. The mass remain the mass. Let's say the mass before it launch is 1,000 kg, right? Yes. Because the fuel is intact, we have not started burning the fuel. V1 is zero, right? That is the initial velocity of the rocket, zero. There is no exhaust velocity yet, right? Now, but when we start burning the rocket, when we start burning the rocket little by little, this is the velocity of the exhaust, right? Yes. Now, what will happen to its mass? Now, when we start burning the rocket, I mean, when we start launching, when we launch the rocket, when we start burning the fuel. Now, when we start, what will happen to the fuel? The mass of the fuel, the mass will start decreasing, right? Yes, the mass of this mass will start decreasing because where the mass of the fuel is decreasing little by little as we burn the fuel, right? Therefore, let's say, for example, before we launch the rocket, the mass was 1,000. So as we launch the rocket, the mass will start reducing. I don't even understand. As the rocket start going up, the mass will start reducing. Let's say from 1,000 to 999, 997, 996. So as the case may be, right? Yes. Therefore, now this DM. So DM DM is the small change. Is the small change in mass of the rocket. Small change in mass of the rocket. Okay, yes, small change in the mass of the rocket. Okay, okay, let me just continue. This small change, DM is a small change in mass of the rocket. So, and please take note, very important, please, this part, and this part is very, very important. Okay, so let me clear this part. Okay, I can clear this part now, you understand. So now, DM. Now, I told you guys that DM is a small change in mass of the rocket, right? DM. Now, when we start burning, please, DM is negative, very important. Okay, so DM is negative, means that DM is less than zero. That means that DM can be -1, -2, -100, as the case may be. DM is what? Is less than zero. So DM is negative, right? Now, since now normal logical sense. Now let's use normal logical sense. Now, when we start burning the fuel, when we launch rocket, the mass of rocket will start reducing, right? Yes, the mass of rocket will start reducing. Now, what will happen to the velocity of that rocket? Velocity of that rocket will start increasing because why? Because of decreasing mass. So just take note that mass of decreases, mass of the rocket decreases. What will happen to velocity? Velocity will what? Velocity will what? Will increase, right? Velocity increases, mass decrease, right? So as you launch the rocket, the velocity of this rocket, normally initially when the rocket was not launched, and when the rocket was not launched, the initial velocity is what? Will be zero, right? Yes. Now after we launch the rocket, now when we start once we launch the rocket, when the rocket start burning and when the fuel start burning, the velocity of the rocket, which was formerly zero, will increase by the v. Okay, by the v. Now the v is what? Is small change in velocity. Small change in velocity. This is very important. Then I told you guys the m is what? Small change in what? Small change in mass. Small change in mass of the rocket, right? Small change in mass of the rocket, right? Yes. Okay. So now I told you guys the is the small change in the mass of the rocket, right? And DM is usually what? Usually lesser than zero. So DM is negative. Okay. Yes. Now what about the V? Remember, see, mass decreases, right? So let's do that. This DM is negative. Okay. Then the V, as rocket starts burning, as fuel start burning, now the velocity of the rocket starts increasing little by little. Now the V is greater than zero. The V is what? The V is positive. Okay, I don't know if you understand. The V is positive, the M is what? The M is negative. Okay, so that will tell you that so so that will tell you that when we launch the rocket, remember I told you guys this is the mass of the rocket initially, right? Mass of the rocket. Okay, this is the mass of the rocket towards the rocket itself and the fuel, right? Yes. Now, when we start launching the rocket, the total mass of the rocket will now be plus the m. Okay, yes. Now it plus dm. Remember, I told you guys that dm is what? Dm is less than zero. That is, dm is negative. Now just imagine. Remember, initially the mass of the rocket. Initially, before we launch the rocket, I told you guys that the mass of the rocket, let's say, is 1,000, right? Before we launch the rocket, the mass of the rocket plus the fuel itself is 1,000. Let's say, for example. Now, when we start launching the rocket, dm now, yes, okay. When we start launching the rocket, this dm is what? Small change in the mass of the rocket. Now, dm is usually as a result of the dm is usually as a result of the decrease in the mass of the fuel. Don't you understand? Because once we start burning once we launch the rocket, the fuel starts burning, right? And the fuel reduce little by decrease little by little. So that decrease in in the mass of the fuel is known as the m. Okay, you remember v is what is the exhaust velocity. Okay, so remember, so guys, now the m is usually negative, is lesser than zero. Okay, it's usually negative, right? Yeah, I told you guys the v is what usually positive. Okay, so if the m is less than zero, that is negative. Let's say is negative, right? So let's say minus 30, for example. So therefore, the total mass as that instant of time, 1000 plus minus 30 is what? Is that 1000 minus 30, right? So 1000 minus 30, that is I think that is 970, right? 970 kg. So let me tell you that as we launch rockets, as the rocket keeps going up, the mass of the rocket will start with the mass of rocket will decrease by what? By the m. Okay, yes, the m is negative. Okay, it's a negative value. Okay, so in every grammar I'm speaking earlier, ever since, just take note that this m is in both the mass of the rocket and the mass of the fuel, right? That is before it initially, before it's launched. Yes. Now, once we launch the rocket, the fuel will start burning by velocity of v. Then the mass will start decreasing by dm, and dm is negative, right? So once we launch the rocket, the mass of this mass will decrease by what? Will decrease by dm. I don't even understand. It will decrease by dm, and dm is a negative value. So therefore, as we launch the rocket, the mass of the rocket will decrease because of the m, right? Yes. So now what will happen with velocity? Initially, tell you guys that initially before launching the rocket, the velocity is zero, right? Yes. Now as we start launching the rocket, the final velocity will be equal to what? The initial velocity, which is zero, plus what? Plus dv, right? Plus dv. So okay, so don't confuse yourself. I'm coming. Plus or plus dv, and I tell you guys that dv is what? Dv is greater than what? Is greater than zero. That is, dv is positive. Dv can be 5, 10, anyone, but as long as it's greater than zero, right? Yes. So therefore, as we launch the rocket, velocity of the rocket will what? Will increase. Let's say dv is, let's say 30, for example. So therefore, the velocity will increase by what? By 30. Okay. So in summary to everything I'm saying is that once you launch a rocket, the mass of that rocket will do what? The mass of that rocket decreases by what? Decreases by what? The m, right? Because the m is a negative value. While velocity of the rocket increases by what? By dv. Dv is a positive value. Okay. Mass of the rocket decreases by what? By dm, right? So this is the mass of the rocket initially, then decreased by what? Dm. Dm is what? Is a negative value, right? Yes. So that is just it. Now what about the velocity? Now, initially the velocity of the body of the rocket is zero, right? Yes, the velocity increased by what? Dv, right? So let's say the dv is 30, for example. So the velocity of the rocket, as you keep on burning the fuel, will be what? Will be 30. So that is just the thing you need to take note. Things you need to take note that is that the mass of the rocket decreased by the m, and the velocity increased by the v, right? Yes. Then why v sub e is the velocity of what? Of the exhaust with which you burn. This exhaust is being born. Okay, this dm is decrease in mass, this small decrease in mass of the fuel. So in summary to everything is that once before launching the rockets, the mass of rockets is remain intact before we burn before we launching the rocket, right? Yes, the velocity initially is zero, the mass is very big. Yes. So let's say for example this is the mass of rockets, and before we launch the rocket, the mass is very big, let's say 1000, right? 1000 kg. Now, but once we launch the rocket, before we burn that what? The m, right? Therefore, and the m is a negative value. Let's say the m is minus 30. Minus 30. So plus minus will give us what? Will give us minus, right? Minus 30. 1000 minus 30 will give us, I think, 170 kg, right? So once we launch the rocket, the mass of the rocket decreased by dm. Then what about the velocity? Initially, the velocity was zero, right? Yeah, v1 is zero initially, right? So as we launch the rocket, the velocity will increase by what? Dv, and dv is a positive value. So 0 plus, let's say 30, will give us 30 meter per second. So velocity increase by dv, while mass decrease by what? By dm. So that is just it. Okay. So that is all about rocket propulsion. Okay. So now this This V, I told you guys, V is what? If they, in a particular question they ask you to calculate for the final velocity of the rocket. Now this is what this change in velocity of rocket. This change in velocity is what? Is V final minus V initial. And remember, I told you guys that V initially is what? Is zero, right? Yes, initially is zero. Okay, so final velocity is just equals so therefore we can also change the velocity, okay, or we can also say V. All right, so we can just say V, okay? We can say V. So this V is what? Is the final velocity of the rocket, okay? Yes. While VE is what? The velocity of the exhaust. V is what? The velocity of the rocket. VE, velocity of the exhaust. This IN is means natural log. Usually in your calculator, okay? Okay, I will show you guys later. Usually in your calculator. Then this M1 and M final. This M1 is means initial mass, M initial, which means initial mass of the rocket, right? That is before we launch the rocket. That is this big M. I told you guys about that. Yes, that is the initial mass, right? The initial mass is large because I'm not still started burning the fuel yet. We have not launched the rocket, right? Yes. So this is the initial mass, right? So what about MF? MF is not what? It's not the final mass of the rocket. After we have launched the rocket, if after the mass after we launch the rocket, this is not the what? This is the final mass of the rocket, right? The final mass of the rocket, and the final mass will be reduced because because of the decrease in mass of the fuel by what? By DM, right? I'll explain that to you guys, right? Yes. So this is the mass in the final mass of the rocket, initial mass of the rocket, which is very large. This one is smaller. Then this is the velocity of the exhaust. Then this is the final velocity of the rocket. Okay. Then move to this other one. So this one is when they ask you to calculate for the final velocity of the rocket. They give you velocity of the exhaust. They give you initial velocity of the. Then they give the initial mass of the rocket. They give final mass of the rocket. So this one is this formula. This first formula. Let me just call it equation one. Used to calculate for the final velocity of the rocket. Okay. Yes, final velocity of the rocket. This one is velocity of the exhaust. This is natural log. M1 mass, that is M initial mass of the rocket, final mass of the rocket. Okay. Don't worry about this one. Same thing. This one is actually, guys, M normally. This is the mass of the rocket before we launch it, right? That is the initial. That is the now this is the mass. I told you guys this is the mass of both the rocket plus what the fuel. While the V, I told you guys the V that is the there is a small change in velocity, okay? So once we launch a rocket, the velocity, the mass of that rocket decrease by dm, right? While the velocity of that rocket will increase by what? Dv. So this is the dv, which is that small increase in the velocity of the rocket, okay? I explained to you guys that the v is positive, while dm is negative. What about this one? V is what? V here. I will tell you guys the presence of this negative value, right? Let's just go to this place. V is what? Velocity of the exhaust. dm, you know, dm. I've told you guys that dm is the mass of the fuel born, right? Yes, that mass of fuel that is born, and dm is negative, right? I explained down to you. So yes, so this is also conservation of momentum, okay? This part is the momentum. This part is momentum gained by the rocket, while this one is momentum carried by the burnt fuel. Okay, so this is the velocity with which the fuel is burned, while this is the mass that is being burnt by that the fuel of the mass that is being burned, while this or yeah the mass of the fuel that is being burned, while this is the velocity uh, of the exhaust of the burning fuel. Then this is the mass of the rocket, the mass of the rocket plus the fuel. Remember, while this one is the velocity with which with that increase in velocity of the rocket. Okay, that increase in velocity of the rocket as we decrease the mass. Okay, so that is just it. So this formula is when they ask you to calculate for either the m. They give you VE, they give us the V, and they give us M. Okay, I told you M is different from the M. I've explained that earlier. Then, yeah, same thing. Yeah, thrust. Just in this place, they just like we add the T to the now for thrust is the force. Remember, force is mass times force is We all know that force is mass times acceleration or mass times velocity times over time, right? Now, this one is still this formula here is still something as this, just that we now have time to it dt. So thrust, which is a force, is equals to this one, which is equals to this. I told you guys, I told you guys that negative value. Now this is negative is because of the m. That the m. I told you guys the m is always negative, right? It's very soon is negative, it's less than zero, right? So it's negative. Can be -1, can be -100, so -30, anyone. So it's negative. Here it's positive because the v is what positive. Okay, so that's just it. Now this formula is different than this, but we add dt to it. So now this dt is a small change in time when there's just an increase, that small change in time when there's a small change in the velocity, that time that time rate, that small rate where there's an increase in small increase in the velocity of the rocket. Same is this the same this the yeah same is in this part here. Yeah, this is the this whole quantity here is the what is that time rate in which there's a decrease in the mass of the decrease in mass of the fuel, right? Yes. So that just see that time, that small time rate when there's a small decrease in the mass of the fuel. This one is small time rate where there's a small increase in the velocity of the rocket. So in everything in all the grammars I've been saying earlier, just know that I've shown you guys that the V is what the exhaust velocity. I've explained it, right? Exhaust velocity. Okay, let me show you guys. So this is the velocity at which the fuel is being burnt. So that velocity is known as VE, which is exhaust velocity. Then I show that one again. Okay, this one is natural log. Okay, it's in your calculator. Natural log. Then MY is what initial mass of what? Initial mass of rocket, right? And this mass is very large, right? Before the rocket is launched, before the rocket is launched, the rocket M1 is both the mass of the rocket itself and the mass of the fuel. So this M1 is the initial mass of the rocket. Then this one M2 is what the final mass of the rocket, right? After we have burned the fuel, after we have burned the fuel to a certain extent. So after we have burned the fuel, right, this is the final mass of what the rocket, final mass of the rocket, right? Yes. Now normally the initial mass is m. We all know, I told you guys that m is both the mass. I told you guys that m is both the mass of the rocket and the mass of all the fuel, right? Yes. So M2 will now be what? M2 will now be this big letter M plus or the M, right? Yes, the M is negative value. The M is the is that I've explained earlier now decrease in that decrease in the mass of the fuel, that little change in the mass of the fuel when we launch when this fuel start burning as we launch the rocket. Okay, so coming. Okay, so that is just so this M2 now be this one. M2 is now the final mass of the rocket, right? Now remember I told you guys the M is negative value, right? So let's say initially this one is 1000 kg. Now final mass now be, let's say dm. Remember dm is negative, but let's say it's minus. Let's say it's minus 100. So plus or minus give us minus. So 1000 minus 100 give us I think give us now 100, right? Yes. So m2 now be now 100 kg. So I'm using this as an example. Okay, that is final mass of rocket. Which now and again. Okay, so m2 is the same as what? mf. Okay, yes, this is initial mass, final mass. So you know this one m. Okay, which is this one here is m, which is the mass of the rocket plus the fuel. The v, you guys know the v, right? The v is that small increase in the velocity of the rocket as the fuel is being burned. Then why this one is that small decrease in the mass of the fuel as the fuel is being burned as we launch the rocket. Mention now and again. Yeah, I think that is all. Remember, so this is negative, right? This is negative. So that is why you see negative value here. Okay, because of the m. The v is what? Positive. So that's why there's no negative here. That's why there's no negative here. Why the t? The t is that small time it takes to that small time rate in which there's a small increase in velocity and a small decrease in the mass. So that is just it. So this taking note of this formula is very easy. Okay, just take note of the formula. We are going to use them to solve. So I think, yeah, the last part of this class before move before move to calculation is coefficient of restitution. Okay, coefficient of restitution. Okay, coefficient of I'm coming. That is the coefficient of restitution. Coefficient of restitution is the measure of the elasticity. So it's a measure of the elasticity of a collision. Okay, of a collision. So coefficient of restitution either tells us whether a collision is elastic or perfectly inelastic. Is whether a collision is either elastic or inelastic or perfectly inelastic. Okay, so the coefficient of restitution is given by symbol E. So this is symbol of coefficient of restitution. Okay, so for an elastic collision, coefficient of restitution is actually 1. Then for an inelastic collision, is actually what, 0. Okay, so what's the formula? Okay, so coefficient of restitution is equals to change in final velocity, over what, change in initial velocity Okay, so coefficient of restriction is the measure of the elasticity of a collision. Okay, so the symbol is usually E. Usually tells us if whether a collision is elastic or inelastic. So for an elastic collision, E is 1, while for inelastic collision, E is 0. Okay, so change in final velocity, so it can is so is V1, so E will be what? E is equals to V1 minus V2. Final, this V is our final velocity, right? While U are the initial velocity. So U1, while for this side will be U1 minus U2. Okay, so V1 minus V2 divided by what? U1 minus U2. So this is the formula to calculate for coefficient of restitution. Okay, so if they ask you, they give you a particular question, they say, is this uh, collision, is it an elastic collision? If you solved and you solve using this formula, this one is the final velocity of the first object, final velocity, this one is final velocity second object, initial velocity of the first object, initial velocity of the second object. So if you solve using their velocity, you get 1. You know that the equation, the collision is elastic. But if you get 0, you know that the collision is inelastic. So now let's move to the next part, which is questions and answer.